Now, as we have already seen that we have taken up an example here, we have obtained our respective singular equilibrium point, then we have obtained the singular points, and we have obtained the different types of eigenvalues here. Now, to find out the phase plane, different types of phase plane, we need to know the different eigenvalues. Now, all total, we have three different categories. First is real eigenvalue. Now, this real eigenvalue can be both positive, both negative, and one positive and one negative. That means if you have a real eigenvalue, supposing you have a system matrix, and by the same process of first finding out the eigenvalue, first finding out the equilibrium point, then the singular point, and finally you find out the eigenvalue. So if you have a real eigenvalue, after obtaining that, you can either have both positive eigenvalues, you can have both negative eigenvalues, or you can have one positive and one negative, just the way as we have got in the particular expression. See, with this particular expression, I have obtained one positive, another one negative. This is one category. Second category will be repeated eigenvalue. In that case, it can be positive, it can be negative. And the third category is complex eigenvalue, where real part is positive, negative, or zero. So you can have in complex also either a positive, negative, or a zero. Just the same way as I was doing the sum, using this J1, I have obtained the eigenvalue which had a complex conjugate with a negative real part. So this falls under this category. Okay. Now, if I take a small example to make you understand the phase plane. Suppose I have an equation x dot equal to 4x minus 3y and y dot equal to 6x minus 7y. Now we have to find out the critical points where x dot equal to 0 and y dot equal to 0. So this becomes 4x minus 3y equal to 0 and 6x minus 7y equal to 0. And this is possible only when x equal to 0 and y equal to 0. So now we have to find out, or rather determine, the behavior of the phase plane using the value or either eigenvalue or its respective eigenvector. Now supposing this is what I get, that is x dot equal to 4 minus 3, 6 and a minus 7 as my system matrix. Now after solving this, like first finding out the equilibrium point, then the singular point, and finally obtaining the expression using the formula, that is lambda I minus the system matrix equal to 0, I find out the value of lambda. Suppose by using this system matrix, rather this is your system matrix, this is my system matrix, like if I use the system matrix and find out that I get lambda, one is minus 5, another one is 2. So what does this mean? This is my exponentially decaying curve and this is growing curve. Now by using these two eigenvalue, I can easily find out the eigenvector, and the formula is Ax is equal to lambda x. So with this, supposing if I have a system matrix, this will be x1 and x2 equal to lambda. Suppose for the first case, if I use minus 5, and this becomes my x1, x2. So using the value first minus 5 and putting the system matrix here, this 4, minus 3, 6 and minus 7. With this and using lambda equal to minus 5, I will get an expression of the first, that is x minus 5 will give me the first eigenvector, which is 1 and 3. Now this will give me a straight line equation y equal to 3x. Secondly, using the same method, if I put the value lambda equals to 2 here, I will get another one, that is another state vector, which is for the value of 2, which is 3 and 2. These two will be my x1, x2, 3 and 2. So this will also create an static line equation 2 by 3 of x. So what do we see here? We are getting two straight line equation. Now with these two straight line equation, if I plot on the phase plane using the phase variables termed as x and y, these are my phase plane, since these are my state variables, so then when I plot it into the respective phase plane, these two will become my phase variables. So if with respective these straight line equation, if I plot the curve at a phase plane, I will be getting a phase plane, or rather a phase portrait. Now what do we do? So we draw phase plane. This is my phase plane and I have phase variables. So now I have two equations. One is y equal to 3x, another one y equal to 2 by 3 of x. Now by using, or rather plotting these two curves, I will be having, like as I said, the equilibrium point will be y equal to 0 and x equal to 0. So with this initial condition, I will be having, or rather I will be getting two straight line equation. Now this one will be for 2 by 3 of x, and you know how to plot this curve, and y equal to 3 of x. So these were my equation, and I have just plotted these two equations into a phase plane using these phase variables. So as I said that this particular equation is obtained when I considered lambda equals to minus 5, and when I am considering lambda equal to minus 5 means exponentially decaying curve. It means that the graph that will be obtained will be having a converging towards equilibrium point, or rather origin. That means this y equal to 3x is obtained by using lambda equal to minus 5, which is actually exponential decaying curve, means actually moving towards equal to 0. Therefore this particular curve which I have obtained here on phase plane, this particular point will have an arrow which is towards my equilibrium point. These two curves will be towards my equilibrium point. And this y equal to 2 by 3 of x is obtained when lambda equal to 2, real positive value. When lambda is real positive value means it's exponentially increasing curve. It will not converge to 0. Therefore, the particular straight line which I have obtained here will be this arrows away from the origin. So these arrows will be away from my origin. So this is the trajectories. Now to draw the phase portrait, what will I do here? What do you see? How does this curve starts? This curve starts from here, following this particular arrow, and then goes out. This is my first. You can draw some more to make a family of phase trajectory. Same way you can also draw it here like this. This is also the same thing. If you want to draw, you can draw the same line here also. It starts following this particular arrow and then goes outside. Same way here, your curve will start tracing the same arrow here and then go out. Same way, some more to make phase portrait. Can you see? This is the way how we draw a face plane or rather a face portrait. So my question was, this was my question given. This is my question given. X dot is equal to 4x minus 3y. Y dot equal to 6x minus 7y. And I have considered this dot equal to 0, y dot equal to 0. And with the help of the same procedure, I have obtained my lambdas, and then with that I have obtained the eigenvectors, and then I have obtained these two straight line equation. I have created the straight line equation, then I have drawn the face trajectories, and then family of trajectories to get a face portrait. So this is how we have solved this equation. So it means that when I was solving the previous question, I had eigenvalue which was for this particular question. This was my question, and I had two equilibrium point, and I have obtained two system matrix. Now in first situation, which was J1, that was having a complex conjugate, that was having an eigenvalue which is complex conjugate. So I'll be coming to this point later. But as I was discussing with you with respective values of lambda equals to minus 5 and lambda equals to 2, which means real, positive and negative value. That means it falls under the categories of one positive and one negative. So same way we'll be solving for this one. When we consider system matrix as J2 and lambda I minus J2 equal to 0, I have obtained what? 0.618, it means real positive value and real negative value. So the same thing, when you will be having the same positive and negative value, same way you will be using a face plane. And then for this particular negative value, for the value negative, you will be having one equation, one straight line curve, and for the positive also you will be having another one straight line curve. For the negative value, the eigenvalue which is considered as negative, those will be having an arrow that is converging towards 0, that means an equilibrium point, and the one which will be having a positive value, that means exponential growing curve, that will have a exponential growing curve which is not converging to 0. So they will be having an arrow which will move outside from the origin. So same way, if you draw the trajectories, then if you want to draw the face portrait, you'll start your curve here following these arrows and it will trace back there. Same way, if you want to draw the curve here, following this line, finally it will go back here. If you want to use these, you can start down here and end up here, and again start here, end up here. This is the way how you draw the face trajectories, face plane, face portrait. So these will be your trajectory. Your face portrait means family of face trajectories will give you a face portrait. The values or the variable which you will be using here, since we have used here x1 and x2, so one will be your x1, x2. These planes are obtained after omitting the value t here. Therefore these plane having a new plane termed as face plane. So the plane is termed as face plane. These variables are termed as phase variable. Curve obtained will be phase trajectory, and then the family of trajectories are termed as face portrait. The next video will be discussing with some more examples, as we only discussed about the real eigenvalue. Next video will be when we have either both negative, when we have real eigenvalue with both positive, when we have repeated eigenvalue, or when we have a complex eigenvalue, positive, negative or 0. Next video we will be discussing with these topics. I hope the video will be helpful for you. Thank you.